All right, thank you, everybody. My name is Thomas. Today I'm going to be talking about elliptic curve cryptography and, by extension, of the elliptic curve digital signature algorithm. So it's broken into three parts. Quick overview of elliptic curve cryptography, really hand-wavy. Then we're going to go into what the elliptic curve digital signature algorithm is and how it's used. And then I'm going to quickly give a real-world example of how you might use this in production or in your sample app or whatever. You can find the slides at that link. So elliptic curve cryptography is just a kind of public key cryptography scheme where it's based on the algebraic structure of elliptic curves. This is different to just modular arithmetic and like exponentiation and other schemes. Some benefits are you have smaller keys. You have to use less bytes to store the keys. The domain is over something called Galois fields, which are finite fields. It's a particular type of mathematics. But this side effect that the maths are more complex than the kind of simpler public key cryptography schemes. Also, elliptic curve digital signature algorithm, which is kind of the main reason why I'm talking about this, allows users to sign bits of data such that they can be mathematically verified by other users in some network or anybody in the world. And this has to do with kind of like a public-private key and their relation. But I'll get into that later. The main idea is that there's this thing called non-repudiation, which means nobody can contest that the data that I say I signed wasn't signed by me. If I say I signed it, you can verify this mathematically, and nobody can dispute this. And this is kind of like the main problem that this solves. Did the data come from me? And we can assert this. So a quick example of the digital signature algorithm in use is I have some message. This is operating, this particular example is going to use the SECP256K1 curve. This is just a particular instance of an equation. It has a few parameters that are defined. It's just a particular elliptic curve. We generate some public-private key pair, and then we sign the data with the private key. Before you sign the data, you usually hash it. So you can see we feed the message and the hash algorithm, give it the private key, we sign this, we get some signature, and then later on we can call the verify function using the same hash algorithm in the public key along with the signature and the message, and then it outputs true that this piece of data was indeed signed by the private key related to the public key. And you can see in these imports right here, I'm using a library called Kryptonite. This is kind of like the de facto cryptography library in Haskell at the moment. So a quick overview of what elliptic curves are. They're defined, a general equation, or a general form of an elliptic curve equation is found here. It's y squared equals x cubed plus ax plus b, with some stipulation that for a cubed plus 27b squared does not equal 0. And this is kind of to preserve this elliptic curve structure such that the curve doesn't loop back on itself and you don't get any like weird intersections. And you can see here there's two parameters a and b to this equation. Coefficients rather. And there's like a quick little table here that shows you as you're modifying these coefficients, they kind of modify the form of the curve or the way that it looks. So a quick overview of what a group is. There's a few properties. So a group is just an algebraic structure that consists of a set of elements over which there's some operation that combines any two elements to form a third element within the same set of elements. It has to kind of adhere to certain axioms, the closure property, the associativity, identity, and inverse axioms. These kind of need to be verified that they hold, but I'm not going to get into exactly what those are. So the reason the groups are important is that we can define a group over elliptic curves. We're going to define some identity element called O. We're going to call this the point of it at infinity. I'm not going to get into why it's called the point of it at infinity. It has to do with some sort of abstract geometry, projective plane stuff, but this is kind of common when you're trying to find groups over equations like this. The inverse of a point on an elliptic curve can be defined as just like a reflection over the x-axis. So as you can see here in this, the third picture, this is kind of a reflection. So in this equation, P and Q, that they're kind of inverses of each other. So you can define this on a 2D coordinate plane, just reflected over the x-axis. So the combination operation of the group is defined with 3 points, actually, P, Q, and R, such that whenever you add them all together, you arrive at the infinity point. This operation is associative and commutative. I say assume it here. You can prove it, but we don't have time for that. So more specifically, you can see that if you take r to be the inverse of the point you're really interested in, you can rewrite this equation p plus q plus the inverse of r equals infinity, such that p plus q equals r. And what this means is basically if I have 2 points, p and q, they intersect the curve at another point r. But because of maths involved in this group, we really reflect that intersection over the y-axis, and really we're interested in that. This is kind of how the addition operation is defined for the group. There's a few other pictures here, but I don't really have time to get into that. This is just kind of an illustration of the way this operation works, and if you have time later, you should go look into that. So actually, elliptic curves that we're interested in are defined over finite fields. They're not defined over the infinite integers. We're interested in curves defined over finite fields, and they can be defined by this 6-tuple, such that p is a ridiculously large prime, a and b are polynomial coefficients to this equation, and there's some generator base point, such that if you take this point and you add any other point in the curve to it repeatedly until you loop back and get the same point g, it defines actually all other points on the curve. Again, this is kind of complex. It's okay that you don't understand it right away, but this is important to the cryptography aspect of it. So actually, elliptic curves over finite fields look like this. They don't look like the previous pictures I had. They look like this because of this finite field, which is basically like a field over a very large prime, and then if you overflow in this field, you just modulus the result of these operations. Yes, you'll generate all of these. Yeah, you would generate all of these points in the entire curve. Yes. What was that?
What are the coordinates?
No, this is just like an x and y field. Yeah, sure. So we talk about this because we care about elliptic curve. We care about public and private key pairs. And so in this elliptic curve cryptography, a private key is actually just some random scalar in this finite field. And then the public key is actually just a point that is resulted by multiplying the generator point by the random scalar k that you generated. So in order for me to have a public-private key pair in this group, I just pick some random integer k, and then I have my private key, multiply it by g, and I have my public key. This is important because there's something called the elliptic curve discrete log problem, and this is why it's this is why it's secure cryptography scheme, because it's computationally infeasible for anybody in the world to find k, given they know my public key q. So just know this is how private keys stay private. If I have a random k and I have a public point q, if somebody has q, they can't find out k, even though they know g and q. So elliptic curve digital signature algorithm is using these bits. It has 2 components. One is to sign the data, and the other is to verify the data. To sign a piece of data is to take a bit of data, combine it with my private key, and then some algorithm, which I'll show next. And then you have a pair, R and S, and this is a signature. And then to verify that is to take the signature, the public key, and the message that I wanted to sign, combine them using some algorithm, and then I can say whether or not the data was signed by the private key corresponding to the public key. This is the algorithm. Not going to go through the algorithm, but this is the algorithm for signing it. The important bit is number 6 that says the resulting R and S from steps 4 and 5 is the signature of the scheme. And so then to verify this data, I combine the data, the signature, and the public key. I run through some algorithm, and then I verify that R equals X mod P, X being generated in step 4. And then I can verify true or false whether or not the bit of data was signed. So quick example, Kryptonite has all this machinery. I'm not going to get into this code, but you can see the sign and verify functions at the bottom. This is important because these are the functions we use in real-world Haskell when we're using this scheme. So here's another module I just quickly defined. This is defining a particular curve we use. People say it's a secure curve, so I'm using it. And then you can see I've kind of wrapped the sign and verify function from ECD DSA module with, I just kind of prefix it with the SHA-256 hash algorithm because we hash it before we sign. And when we verify, we need to hash it with the same hash algorithm that we use to sign it. I work in blockchain. So a quick example, you have a block header. It contains some important data. And then in the body of the block, you can see there's a block header and then a signature. And what I need to do is kind of prove to everybody in the network that that the block came from me. So Okay. And then so you can see we make a block, we sign the block, and then later on you can see in this quick example that we generate a key pair, I have some block data, I make a block with the previous functions that I've shown, and then you call verify block with the block, and then everybody in the network can verify that this originated from me. And quick conclusion, elliptic curve cryptography is complicated, the math is hard, it wasn't really hand-wavy. Elliptic curve digital signature algorithm is useful. And then that there's a lot of real-world applications of this that you can, apply if you want to verify the origin of the data. And that's that.
We have time for one question.
Sorry. So years ago, someone sent me some RSA code, and it worked really well against itself. But when I tried it against OpenSSL, it clearly had not been implemented correctly.
Okay, sure.
So how did you check that I could see you encrypted, decrypted. It worked.
Right, yes. So I'm using the library called Kryptonite. This is the de facto cryptography library. It's implemented by someone named Vincent HaskellX and plus a lot of other contributors. How do you verify these things are implemented correctly? It's really hard. But there's a lot of testing. They have warnings on all the functions that are not tested thoroughly, like whether things are vulnerable to timing attacks. You can kind of fire a lot of data at some cryptographic function and maybe figure out maybe the private key. But these require very sophisticated attack vectors. Yeah, and so this is kind of like, if you want to use cryptography in Haskell, this is the library to use because it's the most tested. And this is kind of an issue you run into when you're implementing cryptography. So. Okay, so that's that.
Thank you very much.
Yeah.